Welcome students on the series of lecture on developing LLM models from scratch. And today we are going to discuss positional embedding. In the last session, we discussed about vector embedding. If you haven't watched the session, please have a look because it is important to think in the terms of dimension. So what we have studied in the vector embedding that every word or every token need to be decomposed into multi-dimensional vector space. So if the word is dog, I'll break the word into a vector which represent different dimension, and these are the weights that will assign to each dimension. Similarly, I'll do it for man. That's what we discussed in the last session. Now the question is, can I use these vectors directly in training any large language model? Can we? Can we directly throw it to the self-attention mechanism? The answer is no. The reason is because what we are trying to do with large language model. In a large language model, our goal is to predict the next token or next word. So if the word is my name and is, these are three words, it has to predict the next token or next word. So just the information about my name is in the terms of vector will not help. What you need to know is the positional information of every word in a sentence, so that you can differentiate between the meaning of a sentence. What I'm trying to highlight is there are two sentences here. Dog bites man, man bites dog. Exactly same three tokens or same three words, but the sequence will change, the context will change the meaning of the sentence, right? So if I only use the vector, then the vector would be 0.01, 0.20, 0.50 for this dog and this dog. There is no change in the vector, the information of the dog, whether it is sitting at position 1 or sitting at position 3. Similarly, there is no difference between the man vector or the information that I'm throwing to large language model or self-attention mechanism, because I'm throwing the same vector embedding, same vector weights. So again, I'm asking the question, is it sufficient to send the information of a vector embedding of a token? The answer is no. So therefore, we need to add some information of the position of each word or each token in a sentence. So the final information that we have to provide is definitely the vector embedding, but plus the positional information of each token or each word, right? So if dog is at first position and man is at third position, if man is at first position and dog is at third position, I have to transfer or I have to embed that information into the final input or the final vector or final weights that I'll throw to large language model. A very simple way to do this is that if I have dog at first position, I will add 1 to all the weights of the vector embedding. So it will become 1.01, 1.20, 1.50, 1.30, so and so forth. Right. And for this sentence, the dog vector embedding, the vector weights will be added with the third position on numeric 3. So it will be 3.01, 3.20, 3.50, and 3.30. And yes, we have embedded all the information about the position. Will it work or not? Okay, it has the positional information. It also has information that whether dog is before the man or after the man in the sentence. That there are certain limitations. And the limitations are, the first limitation is these positions do not have any magnitude limit. It doesn't have a limit. So assume if there is a token which is sitting at 1000 position, then you will add 1000 to these vector. And if you add 1000 to these vector, which has weight of 0.01, 0.020, 0.50, 0.30, what will happen to the information in these vector about the word itself? The position 1000 has overpowered the word information. The position information overpowered the word information because the magnitude of the word vector, the information of word vector was very small, the magnitude was very small. And when you're talking about the position 1000, 2000, 3000 in a positional space, then when you add it, the problem is the information about the word got lost. And the only information that machine can understand, okay, it is at the magnitude of 1000. The second problem is, the second problem that you might not understand right now, till I give you the example, is that the relative position is not intuitively captured in attention mechanism. The relative position may not be captured in self attention mechanism intuitively. It's not saying it won't get captured. It is saying in the self attention mechanism, it won't get captured intuitively. I'll request you all to pause the video here and think about it, let it sink in, let it digest, and then move to the solution of this. Okay? The solution is you can use sine and cosine function to embed the positional information. So if the position is 1, if the position is 1, then you will first try to find out what is the dimension of the word embedding. Say the dimension is, say, 6. So you will do sine 1 cos 1 sine 1 upon 10 cos 1 upon 10 sine 1 upon 100 comma cos 1 upon 100. If the position is 3, you will simply do sine 3 cos 3 sine 3 upon 10 cos 3 upon 10 sine 3 upon 100 cos 3 upon 100. If the dimension of your word embedding or vector embedding is 6, 1, 2, 3, 4, 5, 6. If it is 7, you simply add sine 1 upon 1000 sine 3 upon 1000. That's it. That's it. First of all, you captured the positional information 1 and 3. And you simply add it to the vector embedding. You simply add this vector to the vector embedding, the word embedding that we discussed in the last session. So this is a positional embedding. This is a positional vector. You add it to the vector for the word embedding or token embedding. Perfect. Now the question is, why sine and cos? First of all, it resolved the problem of magnitude. We know that sine or cos always fluctuate between -1 and 1. So definitely the position information will never ever overpower the information of the word. So that problem has been resolved. So the first problem has been resolved. The second problem. The second problem is related to the relative position. Okay. So the first problem is that if you add 1000, then what will happen? Then this 0.02 will become 1000 0.02, and this negative 0.02 will become 999.98. So the information related to the word got lost in the embedding, and the position information dominates, and that's why the sine and cos is the best solution. Now, the second one is, I was talking about that the relative information of two word will not get intuitively captured. What I was trying to highlight. See, if man is before the dog, and for the man I have given the position of 1, and for dog I have given the position of 3. So 3 minus 1 will give me 2, right? So 3 minus 1 will give me 2, and this information is telling me that dog comes after man. And here, if it is 1 and if it is 3, and if I do 1 minus 3, then it is telling me that, hey, dog comes before the man. So the relative information, whether the dog comes before or after the man and at what position, it is getting captured. So what I'm trying to say that the relative position will not get captured. See, I never said that the relative position got never captured. What I said that in the self-attention mechanism, which we'll study in the upcoming session, there the relative position will not intuitively get captured. Why? Because when you will study the self-attention mechanism, there you will see to find the self-attention weight, you're doing a dot product between two matrices. You have to, you will understand that. You're doing a dot product. And dot product will transform these matrix into a different dimension matrix. And that would be the final matrix that you would be using for learning the large language model. We'll see that. Now, if I use sine and cos, because of this dot product which is being used in the attention mechanism, using sine and cosine is giving us additional benefit to intuitively capture the relative information. How come? Do you remember this formula from your childhood days? So if I'm saying 1 minus 3, so 1 minus 3, the relative position. I'm talking about the relative position of two words or two tokens. So if I'm doing sine A minus sine B, if I break it down, it becomes sine A dot product into cos B and cos A into the dot product of sine B. The sine A dot cos B and cos A dot sine B. So can I say if I do the dot product between sine and cos, actually intuitively it capture the difference between the position itself somehow? See what is happening. So the dot product itself capturing the information, the relative information of the position. I don't have to do additional subtraction and addition to find out the relative position. See, the biggest fight in the large language model right now is of what? Is of to decrease the computational cost. And you are saying, let's do the simple subtraction. Add a simple subtraction to find out the relative position. You're adding one layer of computation to find the relative distance between the two tokens. Why? If the dot product itself carry that information. So in the attention mechanism, you have to do the dot product. And dot product between sine and cos carry the information of the relative distances. So what is the need of one another layer of subtraction? No need. And that's why I was saying that relative position is not intuitively captured in self-attention mechanism. You have to perform additional computation, that is subtraction, to find the relative position. Why to do that? Why to put pressure on your GPUs? No need. And therefore, if you study the self-attention mechanism paper, the paper Attention All You Need, the 2017 famous paper, you will find that they talked about the sine and cosine positional embedding. Okay. So we have covered positional embedding in detail, and I think by now you understand the difference between tokenization, the difference between vector embedding, the difference between vector embedding and positional embedding, and now we can jump into self-attention, which is quite exciting. With that, I'll pause here. Thank you. Have a nice day.